Good morning, ladies and gentlemen. It's my great honor to stand here to make the presentation. The title of my presentation today is a preliminary evaluation of OpenPOWER through optimizing stencil-based algorithms. And my name is Jingheng Xu from Tsinghua University. The presentation today will be divided into 4 parts. And first of all, we would like to provide a brief introduction of our research group. And secondly, an evaluation of POWER8 processor was provided. And thirdly, we would like to provide the brief introduction of CAPI Technology, and finally come out with the preliminary example of OpenPOWER based on the CAPI. And our research group is called Tsinghua High Performance Geocomputing Group, and our research target is finding the best computational solution based on the combination of architecture, algorithm, and applications. And the applications we are focusing on include the climate modeling, seismic modeling, and city planning. And as for the platform, we use the CPU, GPU, and DFE, and so on. And there are some partners of our group, including some of them are in academic area, and some of them are in the industrial field. Secondly, we would like to provide a brief introduction of the POWER8 processor through optimizing stencil-based algorithms. And first of all, let's take a quick glance of the POWER8 processor. And in each chip module of POWER8 processor, it is combined with 10 or 12 cores, each of which is capable of running up to 8 threads in simultaneous multi-threading mode. And the bandwidth of each module is up to 200 gigabytes per second. And to evaluate the POWER8 processor, we use 3 general use stencils as our target program. And take Jacobi stencil as an example, we could find out that if we want to get the blue point in the middle, then we need to use the value of all these 7 points and at T point, and then we could get the value of blue point in the middle. And the memory access pattern of this Jacobi stencil and the algorithm could be shown in the right part of this slide. And from the memory access pattern, we could figure out that the remote memory access is frequent, so the cache miss would be one of the biggest challenge of our program. And secondly, from the algorithm, we could find out that the float to byte ratio of this algorithm is quite low. So the program is a bandwidth-bound program. And to fully unleash the performance of POWER8 processor, a set of optimizing techniques was provided. First of all, we use the lightweight turning to figure out which is the best choice of compiler and the optimal compiler options. According to the experimental result, we could find out that the result of XL compiler is far more better than the GCC compiler without advanced tuning. So the XL compiler with the compiler options as shown above is best choice. And then the second problem is how to use the simultaneous multi-threading mode. And as we know, the simultaneous multi-threading mode is an innovation of Power processor, and actually it's just like the hyper-threading of some related company. And according to the analysis as well as the experimental result, we could find out that the latency-bound programs will benefit most from the simultaneous multi-threading mode. And for our stencil-based algorithm, since they are bandwidth bound, so the most optimal performance is get when the SMT is equal to 1. And as for the SIMD vectorization, the main problem of the vectorization is that we should determine how many points we should choose at one time. And there are 2 kinds of methods of the SIMD vectorization, including the GPR oriented SIMD and VSR oriented SIMD. And according to the experimental result, we could figure out that the GPR-oriented SIMD vectorization will come up with a better performance result. And also for the cache blocking method, there are still 2 ways, and according to the result, we could find that the 2D blocking method will come out with a better result, mainly due to more sufficient utilization of the cache elements. And with the optimization, with the tuning techniques we provided, we could figure out that a remarkably performance boost is achieved. And compared with with the related work, we could find that the power could get far more better performance than the related company, the product of related company, and we could get the conclusion that the OpenPOWER is powerful. And finally, we would like to provide a brief introduction of CAPI technology and a preliminary example running on the OpenPOWER with CAPI. Then what is CAPI? As Bruce talked earlier, it is coherent. The CAPI is short for the Coherent Accelerator Processor Interface. And in our case, we just choose FPGA and POWER8 as our accelerator and processor respectively. Then what will happen prior to CAPI? The CAPI is a technology designed for the heterogeneous computing, and prior to CAPI, if an application wants to call the FPGA, then it needs to call the device driver. Maybe it should first generate some variables and input data, store them into the virtual address memory, and then copy them to the device driver storage address, and finally copy them into the FPGA local memory. And once the FPGA gets the output, it should move it back to the device driver storage area and then back to the virtual address memory. And in that case, there are 3 versions of data which are not coherent. And in addition, thousands of instructions in the device driver is needed. Then with CAPI, what will happen? Through the PSL in the FPGA part, we could just the application could generate some variables, store some variables and input data into the virtual address memory, and then it will be the FPGA is capable for accessing these variables. So in that case, there are only 1 coherent version of data, and no device driver call is needed anymore. And to test the performance of CAPI, we use the preliminary example, which is the stencil-based RTM. And according to the algorithm shown in the above of this slide, we could figure out that there are 3 main challenges of this program, which are the memory access pressure, computational pressure, and I/O pressure. And through the experimental result, we could find out that when we use one core of POWER8, the memory access pressure and computational pressure is the bottleneck of the program. However, when we use 20 cores or even more cores of POWER8 processor, the field I/O and other stuff would be the main bottleneck, as we could say in the at here. And to solve this problem, we designed a hybrid algorithm, which is the hybrid algorithm makes that makes the host take charge of the I/O and other part of the program, and make the device specifically take charge of the computational part. And in that case, compared with the original performance and the power optimized performance, we could figure out that the CAPI version would come up with a better result. And in conclusion, the OpenPOWER system with CAPI is makes a combination of powerful host, flexible device, and low latency interface. So it would come up with an extremely high performance as a result. And that's my slides, and thanks for your time.